So in this video, we'll do an example like problem number 34 in the extra practice for 11.7 through 12.5. This is the extra practice assignment to help you prepare for exam 2. So I'll make up some different numbers, but it'll be very similar. So the problem says a company knows that unit costs C and unit revenue R. The words unit aren't super important here, just cost and revenue. From the production sale of X units, so X toasters or whatever they're making, are related by the equation C equals R squared over 218, let's make it 220,000. Oops. 220,000 plus, I'll make up a different number. Let's say 9,714. Okay. And then it goes on to say, find the rate of change of revenue per unit. And in fact, I'll write that here. Find the rate of change per unit when the cost per unit rate of change of revenue. There we go. Yeah. Rate of change of revenue per unit I'll just clean that up. Okay. Per unit when the cost per unit is changing by, let's say, $10. Cost per unit is changing by $10, and the revenue is, say, 3,000. So the first thing I notice reading this question is if I were writing this test myself, or these practice problems, then I would not word this quite the same way, and I'll tell you why. Is changing. The cost per unit is changing by. Well, is it changing up or down? I would assume up, because it might have said changing by negative $10. That would mean going down. So I read it as being a little vague, but I'm going to go with an increase. That's what I would have to work with. I'd have to assume that, although I just don't care for the wording. So just to recap what we have here, the R value is the revenue per unit. Okay, revenue per unit. Okay, and then the C is the cost per unit. Okay, now when we are asked to find the rate of change of the revenue per unit, that's basically the rate of change in capital R with respect to time. That's drdt. Okay, so we're looking for drdt. Let's make a note of that over here. So I'll change the color. This is what I'm inferring from the description. Find drdt, and then we're given two pieces of information. I'm told that the cost per unit is changing by $10. That's dc dt, the rate of change in the cost as a function of time. So dc dt equals $10. And then it says also the revenue is 3,000. Okay, because if the revenue were 5,000, basically the way in which the revenue changes is dependent on a number of things. In part, it's related to what is the revenue right now. Maybe the more revenue you have, the slower it grows over time, because you're kind of running into market saturation or something. You're not going to be able to sell more than a certain number of units. So as you get more revenue, the gains over time start slowing down. Okay, so that's going to tell us that R equals 3,000. Now here's what you have to watch out for. The way I typically write this for like a Cal 1 class, and of course for people who are going to go on to take Cal 2, Cal 3 differential equations, I wouldn't write it this way. I would be more specific because really this is R at some time, right? Time equals 0. Or let's say time equals 1. At some point in time, that's what the revenue would be. In this class, I typically don't go into that detail. I just say, oh, well, this is R. This is the value for R without using this more proper notation. So I'm not going to worry about that here because we don't need to get bogged down in what is the most precise, correct notation. We just need to get, well, how do you do this, right? So what we need to be aware of is I can't just plug this 3,000 in for R just yet because R changes over time, right? The revenue is changing. And so this equation relates R with C at any given point in time, but R is not always 3,000, so I can't plug it in here yet. Now, if I wanted to know, well, what is C at that time? When revenue is 3,000, what are the costs? I could plug it in and find that if I wanted to know that, right? I think my numbers are a little unrealistic. Oh, well, that's fine. Yeah, because this makes costs more than revenue. Well, I guess you're losing money at that production level. So, that's realistic, I suppose, depending on the situation. Okay, so let me get rid of this. So what I have to do is I need to utilize this number. I need to be able to utilize this number before I can plug in the 3,000. I can't plug in 3,000 at the beginning. Now I want to find drdt, so I need to take this equation and apply the derivative with respect to time to both sides of the equation so I can get drdt and dcdt to show up. So I'm going to say I'm going to find dt of c equals dt of r squared over 220,000 plus 9714. Okay. The left-hand side is not too hard. It's just dc dt. The derivative with respect to time of c is just a rephrasing of the derivative of c with respect to time. Just different notation means the exact same thing. I didn't really have to do much there. For this one, though, I need to be a little bit careful. I have to make sure I'm applying the rules appropriately, and I have to use the chain rule because the variable in the expression is not the same as the variable that the derivative is being applied with respect to. In other words, the revenue is a function of time, so I can't just use the power rule. I have to use the chain rule. In this case, my outside function is x squared. Something squared is the outside function. The inside function is the revenue as a function of time. I don't have a formula for that, but that is what I have there. That's what's happening. Revenue is a function of time. So when I apply the derivative, another thing I'll also point out is that I could have written this as like a fraction in front of r squared. I could have written this as 1 over 220,000 times r squared. So then the constant multiple rule would mean that this number just sits here when you apply the derivative. I don't have to do that. I don't have to write it out that way. I just leave, like I could say, oh, I'm going to use the constant divisor rule. Nothing's really called that, but I can think of it that way. I'm really applying a variation on the constant multiple rule. So this is going to be 2 times r, that's the power rule, times, because of the chain rule, drdt, okay, equals 220,000 plus 0 because the derivative of a number is 0. So now that I have gotten dc dt and drdt to show up, I can totally plug in this 10, because that's a dc dt, and I can also now plug in the 3,000 if I want to now find out what drdt is. Now I can plug in the numbers now or later. I think it'll be a little bit easier if I do it sooner rather than later. So I'm going to go ahead and plug the numbers in. So I'll have dc dt, and that was, yeah, this is COs again, so 10. This is 2 times 3,000 for R. Oh, I'm sorry. 10 equals 2 times 3,000 times dr dt over 220,000. I will point out that if I had wanted to, I could have taken this equation and gotten dr dt by itself first, use algebra first. I think it's going to be a little bit more convenient if we plug the numbers in first. The reason being that we could do some cancellation. Since I have a fraction here, these zeros can cancel, right? Cancel them pairwise, top with the bottom. This 2 can cancel with the 220 to make 110. Okay, so now I have 10 equals 3 over 110 times drdt. Okay, then I can multiply both sides by 110 over 3, which would have the effect of canceling this fraction with this fraction. I'll have this total here. So this is going to be 1100 over 3 equals drdt. Okay. So there's my result. Now if I want, I believe this is going to be like 33.333 repeating, but let's get a calculator real quick. I think it's 33 point something, but let's throw this in a calculator, or 33, yeah, 330 rather. Yeah, oh, okay, yeah, I was off by a little bit. So basically, I'm running out of room there, so I'll put it on this side. This is 366 point, I guess I'll round to the nearest cent because this is in dollars. So this is dollars per, the problem didn't give us like hours or minutes. Let's say per day. Yeah, it does not say per day. Let's pretend it's per day just to have a label. It's dollars per day. So this is the amount at which the revenue is changed. It's going up, right? So just to recap, I have the equation that I'm given. I'm given a description, which I have to interpret. I have to come up with these more mathematical descriptions myself from the paragraph description. And then I apply the derivative with respect to time to both sides. Then I plug in my numbers, and then I get drdt by itself. That's the overall process.